All right, great. Hello, everyone. Welcome to the nth week of GROOT, first talk of the week. We'll be hearing from Willow Bevington about stratified homotopy types. So take it away, Willow.
Hey, so I'm going to talk about stratified homotopy types. It's the first talk I've given in a while, so we'll see how it goes. But I think the most interesting thing to point out initially is what the ChatGPT kind of world thinks of stratified homotopy theory. So I've got these three images down here. That's apparently the AI's interpretation of what stratified homotopy theory is. So take that how you will. I think the first thing to cover is what's possibly a bit of a contentious topic within kind of higher category theory is what do we mean when we say space? So for me, there's this like all-important adjunction which kind of defines the notion of space. So we've got over here the infinity category of infinity groupoids, which we'll sometimes call anima or spaces. Mostly we call it anima to annoy people because a lot of people really hate that word. And over here we've got the homotopy category of topological spaces, and we've got this singular simplicial set and geometric realization adjunction. And so for me, this infinity category of infinity groupoids is going to be what I mean by space or homotopy type. Okay. So with that in mind, let's talk a bit about the motivation. Why should we care about stratified homotopy theory? And I think the kind of best argument I've kind of heard in kind of recent years. So there's lots of stratified topology in maths out with the kind of world I work in with things like de Rham cohomology or Floer homology or things like that. But really, the thing that interests me about stratified homotopy theory is its applications in chromatic homotopy theory. So there's these amazing applications of people in higher category theory these days to kind of notice a lot of structures in homotopy theory as arising from stratifications. And I think a really famous example of that is the chromatic tower, which is in some sense a stratification of the sphere spectrum. And you have to make sense of those words, and that's a particularly challenging thing to do, but it can be done. And it's and so if we can somehow understand whatever stratified stable homotopy theory is, then we'll have a better understanding of chromatic homotopy theory, and we'll be just that bit closer to understanding the homotopy groups of spheres. So hopefully, if I have time today, which I think I will, we'll have some time to talk about what is probably like the primary tool of calculation in stratified homotopy theory at the moment, which is exodromy, which is by Peter Haine, Clark Barwick, who's my supervisor, and Saul Glasman. So before I generalize something, I should talk about what it is I'm trying to generalize. And so there's this notion that I think we've probably all seen of covering spaces. But I just want to cover it again in a slightly different language to perhaps what people have seen before for covering spaces. So if you remember recall that the circle can be equivalently described as the complex numbers minus the origin, or at least it's homotopy equivalent to this. And in this second description of the circle, we can see finite covering maps. So finite covers are just given by some kind of, I'm going to call them alpha n, which go from C minus the origin to itself, and it just sends a complex number to the same complex number to the power of n, right? And so, I've got a kind of pictorial description over here, which is exactly what you expect, right? It takes the nth roots of unit e and it sends them all to 1, which will be our base point here. And there's this interesting thing going on here where if you have two maps, alpha n and alpha m, then for n and m not necessarily the same, you can you can compose them, and you can get this is equal to alpha n m, right? So z to the power of n, and then to the power of m would just be z to the n m. And this is interesting because what it means is we've got like a filtered system of these covers in some sense, right? So we can say that we can actually describe alpha n as being less than or equal to alpha m if and only if n divides m. So that's pretty cool. And we can hope, like, if we've got this filtered system, like we can kind of hope that we can take a filtered colimit, and you can hope that you'd get some kind of universal cover. That doesn't quite work out in terms of the colimit. There's some weird things going on now, but we do have something that kind of plays that role, right? We have a universal cover given by what I'll call just alpha affinity from R to C cross. This is why it doesn't quite work out. We've got this R here instead of a C cross, which just sends T in this case to e to the 2 pi T. And so, in some sense, I want to highlight this because, I kind of want to be thinking of alpha infinity as somehow some kind of colimit of all the alpha n. So is there a realm in which we can kind of make sense of that? That's going to be one of the things we're going to be looking at kind of generalizing today. But I want to study these covering spaces a bit more and kind of work on how to generalize that. So I want to talk about something called monodromy, which again, probably a lot of people here have heard of before, but I want to kind of put it in this context, right? So typically the way we talk about monodromy is if you have your base space down here, which for us is just the circle, and this cover up here, which in this case, I guess it's a universal cover. Then if you imagine going around just once, like going around a loop just once in the base space, then you can lift that up here to your cover, and this will become a path here, but you won't end up at the same point, right? So you see down here we ended up coming back to exactly the same point, and it was a loop. But here there's a kind of jump going on here, and that jump is what we'd call the monodromy of that lift, right? And so what is this actually doing? We're taking an element of our base space based at some point x, right? This is our loop down here, and we're sending that to an automorphism of the fiber at x, right? And so this is just literally our covering restricted to this point x. And so what is this map? It's we'll take an element gamma, and we'll take a loop gamma, and we'll send it to the monodromy of gamma, which is exactly this element here. So in this case, this is the kind of +1 element of z, because this fiber is z, right? Now, covers are kind of a bit kind of manifold centric. So we kind of want to think of a way to kind of step away from manifolds and be able to study arbitrary topological spaces. And so the way we can do this is by this like fairly standard construction, I guess, of locally constant sheaves, right? So what we have is locally constant sheaves. Are equivalent in some sense to coverings, and this equivalence could be made very explicit in the sense of manifolds, in that if you have a locally constant sheaf here, you can just create a covering by just taking the union of all of the fibers, all of the germs really, and the equivalence I described up above, up here, can be rewritten as sending a locally constant sheaf, i.e. a cover, to a representation of the fundamental group of the base space, right? And so in this case, it's taking a locally constant sheaf F, a locally constant sheaf of C vector spaces, I should say, and it's just sending a loop in your base space to automorphisms of that sheaf, of the stalk of that sheaf at your base point, right? So it's doing exactly the same thing, it's just a different language. And now we're working with sheaves, which we can kind of apply to any space that we're interested in. So this is exactly the kind of thing we're going to be trying to generalize. So I'm going to try and generalize it to higher categories and then to higher stratified homotopy types. So if we deal with higher monogamy, we no longer have to worry about connected C manifolds, because the problem, so we need to consider connected complex manifolds up here, exactly so that we didn't end up with some kind of issues with this base point, right? So yeah, you could imagine a different cover. I could draw a second part of the cover over here, and that cover is essentially completely ignored by this entire story because we're only considering the connected component of this base point. So normally in homotopy theory, to fix that, we consider groupoids instead of, like, the fundamental groupoid instead of the fundamental group, and that's exactly what we're going to do here. So if we consider, again, locally constant sheaves of C vector spaces, we could just, instead of considering just representations of the fundamental group, we can consider representations of the fundamental groupoid. And you get exactly the same equivalence, but now you just don't require it to be a connected complex manifold. And again, you know, why stop there? If we can do the fundamental one groupoid, why not do the fundamental infinity groupoid? And you just chuck that in, and it all kind of works out. So the locally constant sheaves of now complexes of C vector spaces are equivalent to representations of the fundamental groupoid of X. And you know, you're welcome to go even further and consider just locally constant sheaves of spaces. And you know, these objects get more and more complicated, but you know, this monogamy equivalence still absolutely holds and is great. So now we've got like a nice kind of way of looking at monogamy. We can for complex manifolds, we can try and look at it for schemes. Right, so you know, we've already able to throw it into a whole new area of maths. One question might be, why do we care about schemes? And for me, again, with this kind of chromatic homotopy theory story, I'm interested in schemes because I'm interested in derived algebraic geometry. We found that in higher algebra and in stable homotopy theory, it's often useful to look at like spectra as some kind of scheme, and so developing this homotopy theory for one scheme should hopefully help eventually develop the theory for derived schemes. Okay, so because I'm assuming most people here don't know much algebraic geometry. I know I don't. I would give like a kind of quick discussion of what a cover is in algebraic geometry. These are what we call étale maps. And if you look up the definition of étale map, you're going to be sad. It's kind of frustrating. It doesn't really make a lot of sense. I spent ages looking at it, and kind of eventually the only thing that made it click for me was that when you're considering spec of a field, étale maps from spec of one field to another correspond exactly to like Galois field extensions, right? And this is exactly the analog of finite covers, and you can see this in a bunch of examples. So if you consider, for instance, C as a field extension of R, you know, this is a degree 2 field extension of R, then this exactly corresponds to a cover of R by C, right? In exactly the way you'd expect. But this is only finite extensions. Okay, so I've got this caveat that I need to write here, which is finite étale covers correspond to, well, Galois extensions are finite by definition. So we don't have a notion of universal cover like we did above. Or do we? If you remember, if I scroll back up here, I talked about how it would be really nice to describe this universal cover as some kind of co-limit of these of this filtered system of covers. Well, that co-limit exists in schemes, right? So I can just take it. So what do we end up with? There's this if you take a filtered co-limit of finite groups, you end up with something called a profinite group, right? So a profinite group is an inverse limit of finite groups, which we've equipped with a discrete topology, right? And something nice about these, just a fun little fact, is that G is always a compact Hausdorff totally disconnected space. This actually completely characterizes these, just in case that helps anyone understand what these are. And also, if we take an arbitrary group, call it G, then we can define its completion, which again I'll call G hat, as just the limit of all the normal subgroups of G for which of finite index. So G over N is finite, and we can just take the limit of G quotiented by N, right? So now we've got a inverse limit of exactly these finite groups because they're finite by definition. And this is called the profinite completion of our group G. So we can do this for the fundamental group, right? So if we have a, so I'll leave that on screen there. We can define the étale fundamental group, which is a profinite group, as just the limit over all of the finite étale covers. So finite étale covers. So, you can think here just Galois extensions of fields, if you like, of the automorphisms of this cover over X, right? And the kind of idea behind this is, is exactly the monodromy equivalence I was talking about before, right? So we have before the fundamental group was equivalent to the category of all of the covers of our base space, which is to say that the fundamental group characterizes automorphisms of these covers. And so that's exactly where this comes from. So yeah, why can't we just define the fundamental group as the automorphisms of these covers, I guess is the reasoning there. So, so what happens in the example we've already considered, right? So we've considered the circle, right? What is the étale fundamental group of the circle? Now, if you remember that from your first algebraic topology class, that just ordinary pi1 of S1, or in this case pi1 of C cross, is just going to be the integers. Something weird happens when you consider the étale fundamental group, because of course this is not a profinite group and it's not a finite group. What you actually end up with is something called Z hat, which is called the cyclomatic group, which you can think of, if you like, as just taking the integers and freely adjoining all the roots of unity one by one. Or you can equally think of it as you take the p-adics and you just consider the product of all of them. So these are equivalent. So something weird goes on here. We end up with like a much more kind of strange group. But the good thing about this is we still have monodromy equivalence, right? So here we consider the category of, well, the analogy of locally constant sheaves here is finite étale covers, which we call least for a reason I don't understand. But this is the analog of the category of locally constant sheaves, and we've got this is equivalent to maps from this étale fundamental infinity groupoid, which I haven't defined, but I defined the first part of it. So this is the definition of the first part of it. It's equivalent to maps from this into pi finite spaces. And the reason I haven't defined this is because, in a way, this equation right here is exactly defining it. And I want to kind of emphasize that because this is kind of like the philosophy of exodromy, I guess. It's we want to consider some kind of weird category of sheaves of a certain type over a space, which should hopefully encode some kind of geometry. So the geometry that we're considering here is covering spaces. And we want to think of it as, in some sense, some kind of functor category. And we have to do something weird here. We have to choose a really weird category to map out of. And we also have to consider only pi finite spaces, which, by the way, actually I should define for you. So these are pi n finite for all n, and only finitely many non-zero homotopy groups. So you have finitely many finite homotopy groups, and everything else is zero. But yeah, the kind of the point of exodromy is to take a kind of complicated geometric situation and write it just as a functor category. Okay, so this has kind of all been a lot of motivation of what exodromy is and why we like what kind of tools we'd want to get for stratified spaces, but I haven't yet told you what a stratified space is. So let's move on to that. So if P is so essentially the kind of idea we want to consider is if you've got a space, how can you break it up in a way that you can then put it back together, right? And so the most stratifications in the wild appears a stratification over the integers. So you've got your points, your lines, your 2D spaces, your 3D spaces within it. But we want to do maximum generality here. So we consider any poset you like. So let P be a poset, and we can give it something called the Alexandrov topology, which is that a subset of your poset is called open if it's kind of upwardly closed. And that means, so if we've got P in U, like here, and you've got some Q that's greater, then that has to be in U for all of the Q greater than your chosen P here. So these two subsets here are considered open in Z, but this one's not open because it's not upwardly closed. Right, and this is just a way of kind of topologizing posets, and now we can give a very simple definition of a P-stratified topological space, which is a space with a continuous map into a poset. Right, so notice here that I say a P-stratified topological space and not homotopy type. We'll get to that later. And they're kind of here the analog of locally constant sheaves is going to be a constructible sheaf, which is literally just a locally constant sheaf that respects this notion of stratification. So it's just locally constant on each strata. So at each point in your poset, your sheaf restricts to a locally constant sheaf. Okay, so some simple examples here, because that's a lot of words, but not many pictures. So if we've got the circle, we've got three copies of the circle here, and I'm going to stratify it in three different ways, right? So the first one is I can stratify over the poset, which just has one element. And that's a very boring stratification. I just map every point in the circle up here down to the point. Okay, that's boring, but it's nice to know that trivial stuff still works. And now I can do a slightly more interesting stratification where I've got the poset 0 is less than or equal to 1, which I'm going to denote by 0 maps into 1. So this arrow just means less than or equal to. And here what we do is we send this point here down to 0, and we send everything else down to 1. Right, that's a nice easy stratification. And maybe now you're going to be able to guess exactly what this poset is going to be. But we've got here, we've got 2 points and we've got 2 lines. Okay, so I'm going to draw exactly that out. So we've got the blue point, we've got the green point, which I'm going to call 0 prime. And we've got the orange line and the pink line, which I'm going to call 1 prime. And the poset, okay, so we're going to send the blue point to 0, the green point to 0 prime. But we've got, in this case, 0 is less than or equal to 1, but 0 is also less than or equal to 1 prime. And this corresponds to the fact that you can go from this 0 stratum out into either of these 2 strata here, right? And so that's why we in order for this map down to this poset to be continuous, we're going to need to impose that condition. And so we've got exactly this kind of symmetry here. So this is the poset we're dealing with. Do we have any questions so far? Yeah, good. Okay. So now I'm going to define exit paths, which are going to be kind of your analog of your fundamental groupoid of your stratified space. So this is where the homotopy theory really kicks in. So we've already got a nice notion of homotopy type of a topological space. So why not use it? So we're going to say that the exit path infinity category of your stratified space X, of your P stratified space, sorry, X, is going to be just exactly this fiber product, which is a nice simple definition to write, but what does it mean? So you know, for an infinity category, you have objects, one morphisms, two morphisms, and so on and so forth. In this case, I'm just going to define the first kind of three of those. So the points of this X path infinity category are just going to be the points of X, and the one morphisms are going to be exactly the so-called exit paths from lower to higher strata. So the exit paths are exactly going to be when you go from a lower strata into a higher strata, which defines, in this case, going from blue to pink, it defines this arrow here. Right, so that's the exit path infinity category. And I'm just going to give you a bunch of examples of these because I, partly out of a kind of like a fond memory of a supervision I had where me and my supervisor just spent ages drawing these pictures until I felt like I actually understand something, which was, I think, like the first meeting we had in COVID. So, you know, it's nice. So again, we have these boring stratifications where we just have your space kind of canonically stratified over the one element post set, which is exactly the same for this circle here. And if you remember that this circle had a post set that was given by just this, but we've got a slightly more interesting exit path category here, right? So we've got the green point and the orange point. And the entire kind of point of these exit path constructions is that we've not just got the post set, but we've got the different ways of going from the green point into the orange line, which is we can go from the green point, we can go out this way, or we can go from the green point, and we can go out this way. And we represent this in the exit path by just two lines. And a kind of nice feature about this description is this actually looks like a circle. But, you know, we've got the other stratification here, which I'll draw the post set to remind you. We've got the 2 points, and we've got the two lines. We've got the different ways of going into that. And in fact, if we try and draw the exit path, we ending up with exactly the same post set. So there's an interesting thing to notice here too, right? So we've got over here, we've got two stratifications of the same space. This stratification, I guess, is arguably simpler in the case that you've got fewer points, but this stratification over here is simpler in the case that we don't have any kind of double arrows going on like we do over here, right? So, you know, that's a kind of nice feature. And you can kind of think of this as you stratify over a more complicated post set, you're kind of like spreading out your homotopy, like your homotopy information, and you can deal with one piece individually at a time. You're just going to have more effort kind of gluing them back together. So let's
hey, Willow, can I ask a question about this previous example?
This one
so just, yeah, or the one in the middle, really, I think is the easiest one, but just to understand the exit path category, is it true that like all of the one morphisms will be like distinct paths? So I mean, so for example, if you have a path that leaves the green and goes a quarter of the way around the circle, is that actually distinct from going, you know, halfway around the circle, and they're just related by a two morphism?
Yeah, so it's related by two morphisms. So I kind of consider them as the same in my head because they're homotopy equivalent. But that homotopy equivalence is data. You're right to question that. Yeah. So here, I guess in a way, I'm drawing like the one truncations of these. But that's a very good point. Yeah. So this is a kind of simplified description of that. Yeah.
Then you don't necessarily have a two morphism between the two different ways of exiting. No, you don't necessarily. You can get spaces where that's not the case. Yeah, a surprising amount of the time you end up with just a one category, but yeah, you can do that. Yeah. Thank you.
Thanks. And yeah, so I'm going to do some more exit path categories here, but I'm going to start from here and go this way because I feel like hopefully you're all warmed up to kind of already guess what these stratifications are going to be. So I'm going to do them kind of quickly. So what do we have? We have 2 points here. We have a yellow point and a red point. And we have, so these are spheres, by the way, these are all S2. We have a kind of a blue line and a green line, which kind of form the equator of this sphere. So I can do that over here. So we've got a green line and a blue line, which I could call, I guess, 1 and 1 prime to kind of give you the an indication of what the dimensions of these things are. And finally, we've got the two kind of two-dimensional parts, you know, the kind of cap on the top here, and we've also got the kind of cap on the bottom here. And so, you know, I can call these, I'll call the orange cap 2 because it's two-dimensional, and I'll call the pink cap 2 prime because it's also two-dimensional. And what does the exit path look like here? Well, exactly what you'd expect, right? You've got a map from this yellow point out into either the blue or the green. And so I just draw lines from this yellow path into the blue and into the green. And you can do the same with this red point here into either the blue or the green. And so you can do that. And then, yeah, if you're at one of these lines, right, say if you're at some point on this blue line, you can go either out into the orange part of the sphere, or you can go out into the pink part of the sphere. So again, you have, you know, you can go into the orange, we can go into the pink, and you can do the same here. And there's also, you know, you can go from the point straight into the hemispheres if you want, which you can draw just as these lines here. Right, so that's that exit path, and again, as you might be able to guess here, this exit path will be quite easy to draw as well, right? We've got a point, a line, and then we've got two simplices, which I'll just draw here as orange and pink. And the poset is simply you can go from the red either into the blue this way, or you can go into the blue this way. So we've actually got 2 lines here, and then from this blue line, you can go either into the orange or into the pink. There's only one way of doing each of those. So you end up with this slightly more kind of fun poset, which somehow looks like a, sorry, this isn't a poset, slightly kind of more fun exit path, which looks like somehow like a combination of these two, which is quite fun. And finally, you can do a really weird stratification here where you've got just a point, and then you've got the rest of the sphere, right? So this is, you know, filled in as a sphere, right? So I can draw this as here, and you know, me and Clark have had our disagreements on how to write this, but I think we just eventually settled on we just draw a line with Z in the middle, because there's Z amounts of ways of going from the point into the bulk of this sphere, right? You can kind of imagine a circle's worth of options, and then you can either go out like this, or you can imagine going around that circle and then going out, and those are somehow like not homotopy equivalent, right? And so you've got an entire Z's worth of options here. So this is weird because you've not just got like a yeah, you've got a very, very unwieldy poset here. And so this is really well demonstrates the notion of like, you know, you can have fewer lines over here, but your kind of reconstruction data is going to get pretty awful pretty quickly. And now for those who do know schemes, also, do you have any questions about the spheres before I move on to schemes? Nice. So if we have a scheme X, we can always stratify it by its Zariski posets, which is just literally its set of points, right? Of Zariski points specifically. And an example of this is if R is a local Noetherian ring, a local ring with maximal ideal M, then spec R, if you've done algebraic geometry, you'll know consists of just an actual point M and this kind of I always call them like fuzzy points, but it's like a generic point, and that is entirely in topological space, just a point and an open set. And then in this case, your space here is stratified by just the poset 0 is less than 1, where you send your point to 0 and your generic point to 1, and the exit path just looks exactly like the poset. So not a hugely interesting exit path there. And finally, the last two fun ones, which I'm going to do just because I spent ages trying to draw these exit paths, but I'll go through them quite quickly, so as to not waste time, right? So here we have one zero simplex, we have two one simplices, and we have one two simplex, right? And from the zero simplex, we can go into the blue line either this way or this way, right? We have to choose that way. Same with the pink line, we can either go this way or this way. So we've actually got two maps like this into either of the one simplices from the zero simplex. And you've got the same story here from the one simplexes into the two simplex. You can go either way. And so we can draw this like this. And so we've got this horrible looking exit path category. But if you wanted to, you could stratify the torus in an entirely different way by adding more points. So let me zoom out so you can see both of them. And now I have to draw all the points, so this is going to be fun. So I've got all of these zero simplices, which I won't label. And I've got the one simplices, and you can see this is really frustrating because I start to run out of colors. So I'll start with yellow. We've got the yellow one simplex here, connected to the red one simplex here. And we've also got a dark blue simplex and a kind of light purple simplex behind here, which I'll draw. Which I guess this is light purple enough. I mean, that doesn't look that different, but and we finally got a two simplex over here. And the stratification, I'm just going to draw it out, but you can kind of see where I'm going at the time. You can go from the green point either into the yellow line or into the red line. From the blue point, you can go either, from this light blue point, you can go either into the blue or the purple line. So I think I've done these two the wrong way around, actually. So blue or the purple, yeah, so I should swap these two. There we go. You can go either into the dark blue or you can go into the dark purple. With a pink point, you can go either into the yellow or the red. And with the dark purple point at the bottom down here, you can go either into the dark blue or the purple. And then for each of these one simplices, you can sit there and work out if you want, but you can go into the orange in only one kind of way. And I really like this description because if you remember, this was the exit path for stratification of the circle we had, and the circle kind of looked like these 2 points with these two lines. So this kind of, in a way, exhibits like the sphere as S1 cross S1, just glued with a two simplex, right? And this is what some people call the Morse-Smale decomposition, which if you've done Morse theory, you might see. Right, so there we go. Now we know exit paths and we know posets. So what is a we have a good understanding of stratified topological spaces, but what is a stratified homotopy type, right? And so what I'm going to do, as Peter Haine does, is he defines a stratified homotopy type as an infinity category X with a conservative functor down to a poset. So a conservative functor just means let me highlight over here. So F from C to D is conservative if and only if the image of a one morphism being an iso implies that the morphism is an iso to begin with, right? So remember the implication the other way is quite clear. If F is an isomorphism, then applying your functor to it will get another isomorphism. But going this way is less obvious, right? Just because you're an isomorphism in the image doesn't mean it came from an isomorphism. But if it is the case, then we call your functor F conservative. And I've never understood why this is like a good definition, other than it being equivalent to the other ones and being a really nice kind of categorical definition. So I'm going to give you another way of looking at these that is slightly more akin to the kind of game we've been playing up here, right? So if you remember the way we defined a stratified space, it was by kind of topologizing a poset. We're now going to like infinity categorize a poset, I guess you could say. So if you have a poset P, you can get an infinity category, which I'm going to call SDP, that's for subdivision, whose objects are just linearly ordered finite subsets of P. And the morphisms are just given by, if you've got two subsets, then a morphism. So if you've got two linearly ordered finite subsets, then a morphism is just given by an inclusion of one into the other. Right, and so in particular, for any object of this infinity category, then we have an inclusion map from that object into your poset, which I can write as here. And that what that means in particular is the subdivision of your poset P is in fact itself a stratified homotopy type, right? Because you've got exactly because inclusions of posets are conservative functors, right? If something is an isomorphism over here, then it's actually an equality, and so it's an equality back here as well. And so we can restrict this inclusion here, and we can get something that I'm going to call the stratified nerve, which takes a stratified homotopy type as defined up here, and gives you a functor from SDP up to the infinity category for infinity groupoids. And what does it do? If you have a P stratified space X, then it will take a linearly ordered subset sigma, and it will just send it to hom sigma into X, which is a very complicated definition, but the definition itself isn't so important. What's important is this theorem due to Peter Haine in 2019, that this kind of stratified nerve functor restricts to an equivalence of categories between this complicated definition I gave up here, or like, I guess a simple definition to state, but kind of conceptually not so clear. There's an equivalence of that infinity category with the subcategory of décollages, which is maps from the subdivision of your poset into, sorry, not groupoid infinity, into the infinity category of infinity groupoids, such that those functors satisfy the Siegel condition, which is just that if you have a linearly ordered like chain, then you can write that as, you can apply your functor to just two objects at a time and kind of string them together with this, with these pullbacks. So this is kind of analogous to the idea of infinity categories as both categories satisfying the Siegel condition, categories enriched in something satisfying the Siegel condition, and as simplicial sets. Okay, and that is kind of like the that is the bulk of the talk. I'll very quickly, I guess, talk about exodromy, but just, I guess, to say, because I've only got 3 minutes, that the kind of idea of exodromy is to take the notion of an infinity topos and extend this idea of monodromy to topoi. So if you'll allow me to quickly just say, I guess a topos is some kind of notion of a category of sheaves on a site, then if you can just think of an infinity topos as some kind of like infinity category of sheaves on a site, and then exodromy boils down to just this equivalence, which I'll write down here, yeah, between maps from your topos into finite spaces and exactly kind of sheaves on your space to begin with. So I guess the point of this is you can extend stratified homotopy theory to stratified topoi, and that gives you exactly what exodromy is, an analog of monodromy for stratifications. And I'll leave it there.
Great. Let's thank the speaker for a wonderful talk. So feel free to unmute and clap, or use the clap emoji, whichever you prefer.
Just trying to remember how to end the sharing screen.
And then does anyone have any questions for the speaker? Oh, okay, I have one, but it's maybe not a good question. But so I was kind of wondering about this, like, so you have this notion of like an étal, like essentially the infinity fundamental groupoid, but for étal homotopy types. So is there something like the homotopy hypothesis that says, you know, this is like that somehow characterizes the scheme, or you can recover it up to, you know, whatever notion of homotopy is right?
Exactly, yeah. So there's this kind of like this Friedlander, I think, étal homotopy type, and yeah, a large part of the work of of exodromy with Clark, Peter, and Saul is to kind of get an understanding of exactly this homotopy type. And the really interesting thing about this étal homotopy type is you can define it in exactly the kind of way you might expect with stratified infinity topoi once you define what they are. But it turns out to just be a one topos. You just get a one category, and that one category has geometric points as its objects, and then specializations as points as its morphisms. So it's surprisingly simple. You only get like homotopy one types, which is just bizarre. All
right, so no questions in chat. So maybe let's thank the speaker once more. And I will go ahead and end the recording.